Bismillahirrahmanirrahim. Assalamu alaikum. Today we will continue our topic on aircraft characteristics. This is lecture 8. So, in order have to understand the concepts of the aircraft weights, we do a following example. Suppose an aircraft can fly from point A to point B under following condition: MTOW, maximum takeoff weight, maximum landing weight, and operating empty weight. It has a fuel flow that is 2000 kilogram per hour. It means if we have a flight time of 1 hour, we have at least 2000 kg of fuel. The mean speed, actually it's, you say, from airport to airport speed is 455 knots. An aircraft has to cover a flight, have a distance of 2150 nautical meters, and it has a reserve fuel of 2500 kg. So we need to know first how much flight fuel is needed. It's very simple. It's the fuel flow into the time required to fly. Obviously, since the distance is 2050, the mean speed is 455 knots. So we can calculate the time simply from d over v. T is equal to s upon v, as we used to have at our basic level. And if you multiply by the fuel, this will be fuel consumption. We will have this flight fuel. Then, since we know that maximum takeoff weight is an operating empty weight plus flight fuel plus reserve fuel and payload, so we can always calculate the payload from this formula. So this is a simple example. So this is the payload we will have at the time of, or from that we can calculate how much seat will be provided to this aircraft, how many passengers will book for this flight. Normally, an aircraft have go to its full capacity with all seats being occupied, but sometimes aircraft, or many times aircraft, has also have the limits on the baggage as well as all the other cargoes they are carrying. This payload versus range graph is a very good way of knowing the distance to which an aircraft can fly with the fuel. So this distance is known as the range. The most important factor that influences the range of aircraft is the payload. So if we want to fly further, we need to reduce the payload. So there is a trade-off between fuel to fly and the payload which can be carried. This is the diagram. Range on x-axis, payload on y-axis. And the different points you will know. Point A, point B, point C. What are those points? And in between that, point D and E as well. So let's explain one by one. Point A, the farthest distance which which an aircraft can fly with maximum payload, and it's a takeoff at its maximum takeoff weight. The farthest distance of BR which an aircraft can fly are completely filled. However, the payload can be carried and it is less than the maximum payload. The maximum distance of aircraft which can fly without any payload, it is known as ferry range, and it is at a zero payload. The aircraft can take off at less than its maximum structural takeoff weight. However, the maximum of fuel is this range of aircraft where payload is limited by maximum structural landing weight is the point D. Remember, an aircraft has to take care of two things. One, how much load it would have while it wants to take off, and similarly while landing there is a limit of each aircraft, and it is where two things are designed. Actually, the impact is designed for designing the landing gear. The maximum weight that a landing gear can carry is dependent upon how much aircraft having a weight while landing. So it's very important, and that's why if the aircraft exceeds maximum structural landing weight, it will damage the gear of an aircraft, and maybe it may damage the pavement as well. But it is, if the aircraft get damaged, then it's a big problem. Let's take an example how to calculate payload range graph, how to draw. Example, the weight characteristics of aircraft are 220,000 pounds, maximum structural weight, landing weight 198,000 pounds. All weights are in pounds actually. Operating empty weight 12513. Maximum structural payload. This point is already given to you, 57,000 pounds. Fuel capacity is 75,400. The regulation says that an aircraft must have an added fuel of flying 1.25 hours. As you can see, maybe because of some weather reasons, or sometimes the airport, the aircraft intended to land may be occupied or something, some emergency case. So it at least have 1.25 hours, so that whether it can go to the nearest airport, or it can wait for, if it has enough capacity in the fuel to fly, to remain in the sky. The aircraft has a speed of 540 meters, and the average fuel is 28.8 pounds per mile. So if for 1 mile the fuel required is 22.8 pounds, and this is a very important thing in the context of the problem we are doing right now, or in the context of the payload versus reach graph. So let's see the first point, what is the range at maximum payload. So first we need to know how much fuel is allowed. This is from the simple calculation, and the data that has been given to us, very trivial, and we found that allowable fuel is 37 487 pound. Then we need to know what should be the reserve fuel or the route fuel actually. So in order to calculate route fuel, first we have to calculate the reserve fuel, and it is from that data. uh, Reserve time 1.25, speed 540, and average fuel burn is 22.8, and that's how we will find not only the reserve fuel but consequently the route fuel. And once the route fuel is found, we will know the range simply as the route fuel divided by the fuel consumption. So our first XY coordinate will be 57,969 miles. But before that, we have to understand, we have to calculate the landing weight, whether what we are, the route fuel we are using will not be causing the landing weight above than its maximum structural landing weight. So it's a maximum structural takeoff weight, and we have subtracted route fuel, and this 197,903. Remember, if the route fuel is calculated erroneously, that then it will result in a landing weight, and this situation will not be satisfied, and we have to have a lesser fuel that we have to calculate. So we have to be very specific in our calculations. So the first coordinates will be 57,969 miles for the graph. Now for the second coordinate, so we have to find the payload for point B. Maximum route fuel is this, and then we have, so we'll have range at this fuel will be 2632 miles, and thus aircraft maximum route length is 2632 mile. The payload can be calculated from this formula, 19,087 pounds. So the second point, point B, will be 19,087 and 2632 miles as expected when we reduce the payload from 57,000 to 19,000. The range is been increased from 960. Its range is nearly doubled. Now, what is the ferry range? Again, we'll calculate the distance, and we know that there is no payload, so this is that point. So finally, this is our payload versus range diagram. First ordinate 57,969, point A. Second ordinate, point B, and the third coordinates, and we join, and this is the point. This is our payload versus range diagram. So another characteristics of an aircraft is capacity, and it depends the terminal building as well as all other. Actually, it also, the capacity also helps in determining the passenger that is to be seated in aircraft. That's the number of passenger plus baggage plus cargo can be computed in this. It helps, actually capacity helps in determining the payload 200 pound per seat. Another point is the aircraft noise, and it is effective perceived noise in decibel. Normally, if I ask you what is the unit of noise, it is decibel, but for aircraft surrounding, this is EP and dB, and it is 12 more than the calculated dB. And Obviously, it is because of the machinery noise and jet exhaust. What is a jet exhaust? Whenever you have seen aircraft engine starts, a fireball from the back of an aircraft. This is what we call the jet exhaust. It is very hot. Now the aircraft turning radius, which is most important for standpoint of view of clearance to the building. It is measured from center of rotation to the wingtip or to the nose or to the tail tip, whichever is maximum. So the point is, when aircraft is turning, it should not be touching the end of the building, or in other word, the aircraft parking is so designed that it, while it's turning, it is clear from the aircraft, and it should not touch the building. It should not strike the building. So turning radius, you calculate it from the function of the nose gear and where is n from the steering angle. The larger the angle, the smaller is the radius. The maximum angle, turning angle is 60 to 80, and for calculating radius, design purposes, 50 degrees of flight. So let's see how you find the radius. Very simple. Go step by step. Step number 1. You must note it down this. Divide the aircraft longitudinally. That is, bisect it from the center of the nose to the center of the tail, and this is your x-axis. Y-axis is very interesting. For drawing y-axis, this is the gear, this is landing gear, what we call double tandem, right? So it's a tandem gear, and then what you do is to bisect it by drawing the center line like this. So what do you think? What what should be the pivot point? Is this a pivot point? Or ideally, if I want to draw a circle, this should be the pivot point, but not while determining the radius. There is another thing. Since we have considered here the landing gear, but what is the contribution of the nose gear? Because the nose gear is the one that is turning, and that is making the aircraft move in this particular path. So we must have some line from it as well, from some axis as well. So what you do, since the aircraft wants to turn at this point and the wheel of the nose gear is at this point, so we'll have a line bisecting this as well. So this will be third line. Now, this is our pivot point. Now what we need to do, we'll check it from this point to this point, one radius, from this point to this point, another radius, and from this point to this point. Actually, we need to do the extreme of the distances. The maximum distance will be our, let's see, from the nose, this radius, and we try to draw a circle. This is a radius of an aircraft. Is it okay? No. Let's try from second thing. And this from the tail tip. Is it okay? Yes, maybe. But we need to check all of the distance. Sometimes it is possible that the nose tip, the tail tip will have a larger radius. It depends upon the length of an aircraft. And also, we'll have a third radius from the wingtip. So we'll take the maximum radius. We'll say mention that this aircraft has the maximum radius. Our aircraft having a more weight will this wingtip will be dominant, but it should not be assumed everywhere. The aircraft may have a longer length, so it may be the nose or from the tail. Sometimes the landing gear is the main landing gear is shifted. So don't be surprised if you have a pivotal radius from the nose of an aircraft. So that's why we have to check, explore, exhaust all the options available to us. Don't assume that since this in this diagram we have got the maximum radius, so we'll always try the wingtip option. It's not correct. We have to exhaust all our options. The nose gear. Now for nose gear, we have to draw a line bisecting the previous line from the wheel to this, and the nose gear is measured from nose angle is measured from this y-axis and the line draw like this. So this is called a nose angle, and it is 60 to 80, but for design purpose it is 50. So that ends my first part. As during the lectures I was told by the students that we must have videos in parts so they can concentrate on one part each. So let's stop here, and we will have part 2 after this lecture. So we'll have a short break, and we'll record news part 2 uh, discussing airport site selection.